Okay, we're doing problem 3062. While studying a coil of unknown inductance and internal resistance, you connected in series with a 25-volt battery and a 150 ohm resistor. You then place an oscilloscope across one of these circuit elements and use the oscilloscope to measure the voltage across the circuit element as a function of time. Across which circuit element, coil, or resistor is the oscilloscope connected, and how do you know this? Well, if the oscilloscope was connected across the inductor, it would start off high and go low, whereas if it was connected across the resistor, there would initially be no current, since there's an inductor in the circuit, and inductors resist change in current. So initially, with no current flow through the resistor, voltage drop across the resistor would be 0, which we see right here, and then level off towards its final value, which it does. So the oscilloscope is connected across the resistor. B. Find the inductance and internal resistance of the coil. Well, if there was any internal resistance in the coil, this graph showing the voltage drop across the resistor would not level off at 25 volts, which you can see clearly does level off at 25 volts. If there was any internal resistance in the coil, then there would be a separate voltage drop across that, which added to the voltage drop across the resistor would equal 25 volts of the battery. Since the voltage drop across the resistor equals the voltage of the battery, there's no internal resistance in the inductor. To find the inductance, we actually have to do a little work. So first, we use this equation. VR equals Vmax 1 times quantity 1 minus e to the negative t over tau, where tau equals L over R, inductance over resistance. So when t equals tau, that's a nice easy number to work with because it works out to e to the negative t over t, or tau over tau, which goes to e to the negative 1, which is, and that gives us this equation, VR equals Vmax times 1 minus 1 over e. So VR equals Vmax is 25 volts, the voltage of the battery, times 0.63, which is 1 minus 1 over e. So VR equals 16 volts. Now we can use VR to find t. T equals 0.5 milliseconds, which is tau, because remember, we solved for when t equals tau. And tau, as I said earlier, is equal to L over R. Now we know R, and now we know tau. So now we can just solve for L, which gives us 75 millihenries. So that is the answer to part B. Now the final question. Carefully make a quantitative sketch showing the voltage versus time you would observe if you put the oscilloscope across the other circuit element, resistor or coil. Well, we know the other circuit element is the coil because we proved earlier that this was the voltage as a function of time across the resistor. So when you plug an inductor into a circuit, it resists the change in current. So if you have no current initially, and then you plug it in, right when the switch is thrown, there's no current. that means the voltage drop, there's no voltage drop across the resistor, but it's still a circuit. So the voltage of the battery minus the voltage drop across the circuit elements must be equal to 0. So we know that it's going to look like this. The voltage drop across the inductor is going to be 25 volts right when the switch is thrown, right here, t equals 0. And then it's going to level off and approach 0 just as this approaches 25 volts.